This is problem 13 of the QHack 2023 Quantum Coding Challenges, and this one is entitled The False Proof. And in this problem, we're given this backstory about this proof where it's shown that 2 pi over 3 is equal to 4 pi over 3, which is obviously wrong, but this is just a preamble for the actual problem that we need to solve. So that's what I'm going to describe here. So what we really need to do is we're given a unitary U, and that unitary U can be one of two possible options. It could be either an RY gate with a rotation angle of 2 pi over 3, or an RY gate with a rotation angle of 4 pi over 3. And what we're being asked to do is to figure out which of these two unitaries was given to us. But the caveat is that we only get to do this with one shot. So we can't implement a circuit and run it several times and get statistics to find out what gate was given to us. We need to do it only with one execution of the circuit. Now, the freedom we're given is that we can apply this unitary U as many times as we want, or a controlled version of this unitary U, and we can apply it as many times as we want. So the first thing we need to realize here is that this problem cannot be solved if we use only one qubit. So we might be tempted to say, okay, I'm just going to apply one of these unitaries or a few of these unitaries into one qubit, and then add some other unitaries to try to rotate things so that if we apply the one with the 2 pi over 3 angle, we get state 0, and if we apply the one with the 4 pi over 3 angle, we get the state 1 with 100% probability, so that we only use one shot. And the reason we can't do it just with one qubit is because if we look at the block sphere, so let's focus here only on the XZ plane here. So this one I'm highlighting here. So if we apply this Ry of 2 pi over 3 to, let's say, the state 0, what we end up with is a state vector pointing in this direction, and this is about 120 degrees from state 0. So it's a 120 degree rotation if we apply this Ry of 2 pi over 3. Now if we apply the Ry of 4 pi over 3, we end up with a state vector in this direction. So this is if we apply this rotation of Ry 4 pi over 3. So as we can see here, these two state vectors are not orthogonal to each other in the block sphere. For them to be orthogonal to each other, they would have to be pointing in opposite directions, right? So in the case of this orange vector, to have a state vector that was opposite to it, we'll have to be pointing in this direction. So there's no combination of unitaries that we can apply to these two state vectors to have one pointing in the opposite direction of the other, because unitaries preserve inner products. So if we apply the same unitaries to these two state vectors, well, we're just going to rotate them by the same amount about the block sphere, and the angle between the two of them is always going to be the same. So the other thing we can show is that even if we apply this unitary U several number of times, we can see that there is no number of repetitions that would lead to having these two state vectors pointing orthogonal to each other. So if we apply the 2 pi over 3 gate, let's say 5 times, and the same amount of times for the 4 pi over 3 gate, there's no way to have them point in opposite directions. So all this is to say that we definitely need at least 2 qubits to solve this problem. Now, given 2 qubits, there are at least 2 ways in which we can solve this problem. So first, one thing we can do is precisely the same thing we just described with 1 qubit, but with 2 qubits. So basically apply combinations of this Ry gate and CRY gate and some other unitaries to guarantee that the two states have some level of orthogonality, or that we can distinguish the two of them from one another. So for example, find the right combinations of gates that if we apply the gate with the angle of 2 pi over 3, we would end up with a state vector like this one of alpha 0, 1 plus beta 1, 0. And if we apply 4 pi over 3, we would end up with a state vector of beta 0, 0 minus alpha 1, 1. So in that case, if we perform one measurement with one shot, if we measure either 0, 1 or 1, 0, we know for sure we have received the unitary with the angle of 2 pi over 3. And if we measure 0, 0 or 1, 1, we will know for sure we received the gate with the angle of 4 pi over 3. Now, I don't want to spend too much time explaining how this could be done, because I think the second option of figuring out how to find which gate we're given is a lot more interesting. But here I just have an example of a possible solution. And here what we end up with is, if we are given the gate with angle of 2 pi over 3, we end up with this state that has a superposition of 0, 1 and 1, 0. And if we are given the gate with the angle of 4 pi over 3, we end up with 0, 0 and 1, 1. And that's just applying one of these unitaries and one control version of it. Now, if we didn't want to end up with superpositions for any particular reason, due to the symmetry of this problem, there's actually some unitary we could apply to after this circuit to not have a superposition, but actually be able to distinguish these two states as 0, 1 if we are given the gate with 2 pi over 3, or 0, 0 if we're given the gate of 4 pi over 3. And here highlighted in green, I'm showing the gates we will need to apply to perform that rotation. Here in Penny Lane, I have implemented precisely this circuit just to show you that it actually works. Now, as usual, I'm importing Penny Lane as QML, NumPy as MP. I'm also importing here SymPy to display some matrices, but we're going to do that later. But down here, what I have is the circuit I just showed you. And if we just execute this and apply a gate where we have an angle of 2 pi over 3, we can draw the circuit. So we have here a single rotation of 2 pi over 3 and a control rotation of 2 pi over 3. And if we just perform a measurement and sample one time, so here you can see in this device, I'm only using one shot, we can see that if we're given the gate with 2 pi over 3, I'm always measuring 1, and I can just re-execute this, and you can see that I always get a 1. And if now I apply the gate with the angle of 4 pi over 3, I always get a 0. And you can check this two are the exact same circuit, where the only gates I've replaced are the ones with the two different angles. Now, let's go back and see what's the other way we can solve this problem. So the second option we have to solve this problem is to use phase kickback. So hopefully you're familiar with the concept of phase kickback, but if you're not, you'll see it in action in this particular problem. And the first thing to realize is that if we take these gates, these unitaries that were given, and we apply them 3 times, and you might wonder, well, why 3 times? Well, because if you see the angle that we're given for the two gates is either 2 pi over 3 or 4 pi over 3. So if we apply them 3 times, in the first case is equivalent to applying an RY gate with an angle of 2 pi. And in the second case is equivalent to applying an RY gate with an angle of 4 pi. So you may say, well, I'm just rotating about the y-axis in the block sphere either once or twice. So that's just like applying an identity in both cases. Well, that is partly true. The difference is that if we apply just one rotation of 2 pi, we end up with an identity gate, but it has a global phase of -1. And if we apply an RY gate with 4 pi, so 2 rotations about the y-axis in the Bloch sphere, we end up with an identity gate with a global phase of 1. So even though for a single qubit, these two gates are exactly equivalent because we can measure global phases, if we use phase kickback, so if we use a second qubit where we implement the phase kickback protocol, then we will be able to extract this global phase, right? So if we make this application of 3 gates into a unitary and then make this a control gate, then we can extract that global phase, right? So let's take a look and see how to do that, right? So if we have this Hadamard gate control unitary where we apply 3 times either the gate with the angle of 2 pi over 3 or the one with the angle of 4 pi over 3, and then another Hadamard gate. Well, since these are identity gates, no matter what state we apply here at the input, well, for an identity gate, all state vectors are eigenvectors of the identity, and they all have eigenvalue of 1. And for the minus identity, they have eigenvalue of -1, right? So this means that if we apply this circuit, we will measure a 0 here on the top if this U is the identity, and we will measure a 1 here at the top if this U is the minus identity. And if that's not clear, let's take a look at it step by step. So in the case where U is the identity, well, that's like having 2 Hadamards and a control identity, right? But what is a control identity? A control identity is if my control is 0, it does nothing, which is an identity. And if my control is 1, well, it does nothing too. So it's like not having any gates here, right? And then if I'm applying 2 Hadamards back to back, we know that the Hadamard is the adjunct of itself. So they just cancel each other. So basically, if I have the this unitary U equal to the identity, which is equivalent to applying this Ry of 4 pi over 3 times, then I will always measure state 0 here at the top. Now, in the case where the unitary is the minus identity, so if we're applying this Ry of 2 pi over 3 times, well, what we have is a control minus I gate. And the reason I'm using this kind of funny symbol here is because this is what is used in Quirk for what is called the negate. So it's basically just negating the amplitudes of the state. So applying a global phase of -1. But now if we analyze this circuit step by step, what we can see here is, well, here at the input, what do we have? We have 0 tensored any state vector psi. Now, if we apply the Hadamard gate, what do we have here? Well, we have 1 over root 2 state 0 plus state 1 tensored psi, right? This is the same as 1 over root 2 0 psi plus 1 psi, right? And now if we perform this control minus identity, what do we have here? Well, 1 over root 2. Now, if my control qubit is 0, well, we don't apply this gate, right? So nothing happens. So we just get state psi at the bottom. But now if our control qubit is 1, well, we apply this minus identity. And the minus identity, all it does is it adds a global phase to this part of the state of -1, which now in the complete state vector is now a relative phase, right? And now here at the end, if we apply another Hadamard gate, well, we can, before applying the Hadamard gate, we can again factorize this as 1 over root 2, 0 minus 1, tensored state psi, which is equivalent to having state minus tensored state 0, right? So if now we apply a Hadamard gate to this state minus here at the top, well, here at the output, all we're gonna end up with is state 1 tensored state psi. So when we apply here an identity, a control identity, which is the same as a controlled version of applying 3 times ry of 4 pi over 3, we get state 0 tensored psi. And when we apply this minus identity, which is 3 times this ry 2 pi over 3, we get the state 1 tensor psi. And this psi can be anything, right? So here we can just replace it with state 0. So this could be state 0, this could be state 0. So now if we sample this circuit only once, all we need to do is just measure the stop qubit. And if we get 0, we know we have ry of 4 pi over 3. And if we measure 1, we know we have ry of 2 pi over 3. So this is really, really interesting. I really like this problem. It's one of my favorites in this QHack coding challenges. So now let's go back to Penny Lane and code this up. But now we have the solution, so it shouldn't be too difficult to do. So the first thing we can do is let's actually just implement a circuit where we apply an RY gate 3 times. So it only has 1 qubit. And I just want to show that if we go ahead and this angle of 2 pi over 3, we get a minus identity matrix. So here we have just a circuit with the 3 RY gates and the angle of 2 pi over 3. And we get an identity with a global phase of -1. And then if we do the same, but with the phase of 4 pi over 3, we get an identity, and here's the same circuit, but with just a different angle, right? So I'm just calling this same circuit QN that I define here, which is applying 3 gates. So now to implement the phase kickback protocol, what we need to do is, well, let's first define a device with 2 qubits, and we're going to perform only 1 shot, right? And let's define our Q node and our circuit that's going to receive an angle of theta. And then we do, as before, Hadamard gate on qubit 0. Then we need to apply the controlled version of this 3 applications of the RY gate. But what is that? Well, if we decompose it, it's like applying 3 controlled versions of the RY gate. So that's equivalent to, you know, bundling up the 3 unitaries and applying a control on that matrix is the same as applying a control version of that rotation 3 times. So we can go ahead and do that here. So I'm applying 3 times to the same qubit or the same control qubit with the same target qubit, an RY gate with an angle of theta. And then again, Hadamard gate to qubit 0, right? And we'll draw the circuit so you can see it. It's the same circuit I was showing in the derivation, but we'll draw it here. And then we're just going to take a sample of wire 0, right, where the phase kickback happens. And that's the only qubit we need to measure. So now let's go ahead and draw the circuit and evaluate it for an angle of 2 pi over 3. So here we have it. So we have our Hadamard. We apply 3 times this rotation gate. In this case, we're passing the angle of 2 pi over 3 and then another Hadamard. And we can see here that the execution of this circuit gives us a measurement of 1. So when we have 2 pi over 3, we'll always measure 1. And if I repeat this, you see I always get the same answer. I always get a sample of 1. And then now let's do that for the circuit with the angle of 4 pi over 3. And if we execute that, we have the same circuit, but now the angle is different, right? And we always measure a 0 in this top qubit. So if I execute it over and over again, I always get a sample of 0, right? So that's it. So the way this is implemented in the QHack problem itself is slightly different, because what we're given is not the freedom to apply this RY gate here ourselves. We are told that our circuit receives that unitary U. So it's going to look slightly different, but it's the same concept. So I'm just going to copy and paste that solution here. So first of all, we define the same type of device, but for the grader, they have to use these additional operations to add that unitary and the control version of the unitary that we're given. But then after that, you'll see that the circuit looks exactly the same, but instead of passing an angle, we're actually passing this unitary, which could be that RY gate with 2 pi over 3 or 4 pi over 3. It's just that I believe is being passed in the form of a matrix, not in the form of a gate. I'm not entirely sure. I'll have to check the grader code. But in any case, as you can see, it's the exact same circuit. We're just applying the Hallamard, a control version of that unitary U, which could be one rotation or the other, so 3 times, and then the Hallamard gate. And then we're asked to also create a function that pause processes the answer. And here I'm sampling both qubits, but as we showed, the only one that really matters is the top qubit. So in the post processing step, we can just say, okay, check just from this measurement result, which is going to be the result from this circuit, just check the first answer, which is qubit 0, and return a value of 2, which is what we're being told to do. If we are given the gate with 2 pi over 3, we're supposed to return a 2, if not return a 4. And then I'm here just going to copy and paste all the code we're given for the grader, and here is just running to check that the code actually works. So it takes a little while because it has several checks that happen. So here we can scroll down to the bottom and see that the answer was correct. So I hope this was helpful, and let me know if you have any questions.